All right, let's see how y'all did. If you type it into y1, 3 times x minus 4 to the 2/3 power, which, by the way, if that could also be written, as y'all know, as the cube root of x minus 4 squared. Your calculator has a root button, but I would recommend that you don't use that. When you're typing something in, it's easier just to write it as a fractional exponent. Okay, so then if I had it with the radical, I would write it like this. All right, so now if you sketch graph, it kind of looks like, you know, back when you were little, I guess every elementary school kid draws the seascape, right? You draw, there's the beach right there, something, there's a palm tree, but you got the water, and then there was the sun. Maybe the sun was orange, right? He was in the corner, and then you either did your rays like long, short, or sometimes you did like squiggly, right? Because so you can like see the vapors. And the sun, of course, he was always cool, right? So he was always wearing sunglasses because it was bright on the sun, right? And then you had your water down here, and then maybe you'd put like a shark in there or something, right? I don't know. I'm just having a good time. It's National Boyfriend Day. Yeah, and then here would be the palm tree, right? And then you'd have the green. Let me hang on. Just this is fun, right? There's the palm tree, but no seascape was complete until you put the birds. One there, maybe one a little smaller, and that finished the seascape. So why is it relevant? This is the graph of those birds. Okay, the parent function is y equals x to the 2/3, and that will be a parent function when you go to calculus. So you're expected to know it, and so that is what I call the bird graph, right? It looks like that at the origin. So now that you know if that's what the parent function is, notice it is kind of in standard transformation form. Inside the x, we have minus 4. What's that going to do to any graph? Move it right 4. So this is like a vertex. It would go right 4, and then the minus 2 outside would move it down 2. So if you used your calculator to find this minimum value, you should have gotten it to be at a really nice coordinate, 4, -2, right? And you, nines and zeros. Yeah, we're going to look at that because your calculator's stupid, okay? It doesn't do any thinking, and yeah, it doesn't always give you the right answer either. So let's see. Yeah, why have it? Because it's good, but you're the boss of your calculator, not the other way around, right? So you have to interpret your calculator and know when it's wrong. All right, so in Zoom 6, we see this. We'll go to second trace. I'll use the minimum key, and left bound, it looks like I'm to the left, so that looks good, somewhere there. You can hit enter. Did you know that you don't even have to scroll? If you want to just type in like you're right bound, if you just want to type in like a number that you know is to the right, like 8, it saves you from having to scroll. But scrolling is sometimes fun, right? Because you can imagine you going, whee, right? Like you're writing. And then for your guess, remember, you just use the left bound, or the right bound, sorry. So it's scanning that interval. My calculator is pretty slow, and it gives me that. All right, so we have to know when your calculator is wrong. It's saying it's 4.0017 and negative 1.99999999565, whatever. That's your calculator's way of saying 4 -2. If you ever see a sequence of 3 zeros or 3 nines, at least, I would say at least 3 zeros or 3 nines, at least. More is better. And then after that third 0 or 9, there is a number that is almost 0 like 1, or a number that is almost 9 like 8. That is your calculator's way of saying, hey, boss, this is the best I can do. I'm working for you. I'm getting paid, you know, but you're the boss. You make the big bucks to make the big decision. So, you know, you got to interpret my work. I don't know. I'm getting back to work. And you're like, okay, thank you. And you have to say, okay, good work. There's numerical evidence to conclude that it's actually 4, because I have at least 3 zeros. I have a lot more than 3. And then negative 1.999, and then there's a 5. So I'd be more comfortable if that 5 were, you know, bigger, but that is 4 -2. And then, of course, you have the equation also, because you're very perceptive, right? You look at all things, and you're like, oh, okay, yeah, right 4, down 2, that makes sense. So that is the answer. So let's go ahead and write it then. We could say that U has a, oh, that sounds awful. U has a local, U has a local min of y equals -2 at x equals 4, and you also has a what? Absolute min, or just a min of y equals -2 at x equals 4. Good. Yeah, you can do it in one sentence. U has a local min and a min, or local min and global min of y equals -2 at x equals 4. Yeah. Do we have any others? Any other extrema? Any local maxes or absolute maxes? No. Okay. U has it. So we're done. You could say no local, or remember, if you use local, you want to stick with global. If you use relative, you kind of want to say absolute. No local or global maxes. Maxes? Is that the plural of max right there? The abbreviation for maximums is, I don't know if I've ever done it. Maxes? Yeah. ES? I guess so. Yeah. We'll make it up. Okay. I know it would be maximums with just an S at the end, but maxes. Okay. Good. So now we'll move on to this last one together. This one's kind of freaky. Not really. So let's go back to Y1. We'll clear it out. I'll do this one with you. X, and then radical is pretty easy. That's just square root. So you don't really have to write that as all that to the 1/2 power. But you certainly could. X minus x squared. So I very seldom, if ever, hit the actual graph button in the top right corner. I'm used to sketching things by just hitting zoom 6. Very rarely do I hit graph. Only when I'm toggling maybe back and forth between home screen and graph. And you know how to use that? Good, because I don't. You have to use a handheld calculator on a test if it's a calculator. So if you have a handheld Inspire and you know how to use it, great. If you're using your TR Inspire app on your iPad that the district purchased, won't be able to use that. Okay? Yeah. Yeah. Right. So I'm waiting and I don't see anything, right? I'm like Jim Adler. I'm waiting. You know, yeah, good. I carry a big hammer. I'm waiting. And then his son comes on. I'm waiting. Oh, that's so cute, Junior. I see a little bit of activity right there. Do you see it? There's a tiny little bit right there. So we need to go in for a closer look, right? So everyone put your face closer to the screen. That didn't quite work. Right, yeah. We're going to have to zoom in. All right, so there's a zoom button right at the top middle. Hit zoom, and you have all these options, right? Zooming in is not bad. Zooming in zooms in by the same scale on the X and Y. But one of my favorites is zoom box. Zoom box, that's number 1. Okay, so what you do for zoom box is it starts at the origin. You define a corner of a rectangle that you want to zoom in on. I always start in the top left, so I'm clicking up a little bit and to the left. And then I'm going to hit enter. And then it's kind of like a pinch drag. You're going to scroll to the right to define the width of the box that you want. And I'm going to go to the right until it contains that little blip. And then you pull down to make the box have depth. You can also go down first and then to the right. And you could establish any corner first. It's kind of nice. You establish one corner of a rectangle, and then you use your directional pad to contain the field in which you want. And the reason this one's kind of nice is because notice my rectangle is longer than it is tall. It'll rescale it to that window. So then you just hit enter. It said error? Oh, maybe you have to start in the top left corner. And it still didn't work? You can also do zoom in. Zoom in. If you just go zoom in, you just got to move your cursor to the middle. Let's see. So did you do that? Let's do zoom box, up, over. You got to go a little bit over and then hit enter. So that establishes the corner. And then we'll click to the right. And then we'll click down just until we see it. And then we hit enter. Yeah, there we go. You hit enter to lock in that corner. And then the only time you hit enter again is when you have your box and then it zooms in. All right, so it looks like that. All right, so, okay, sweet. If you want to transfer this to your paper, that wouldn't be bad. It looks like it goes like that. Yeah, cool. Now, where does it start? At what value of x? In other words, like, what's the domain of this? Yeah, it goes from 0 to 1. And you could solve that the way we've done in the past. X minus x squared has to be greater than or equal to 0. And then you can graph that parabola. Or you can just kind of use the calculator, right? If you plug in a 0 for x, you get 0. If you plug in a 1 for x, under the radical, you get 1 minus 1 is 0. So it does go from 0 to 1. But there is a high point right there. And by high point, I don't mean like friendly point, like, hi. Although that would be a good place to stand to greet people, right? We need to find it. So let's go second. Trace! Oh! Yeah, I know. $100 pens keep dropping. But they keep working, so maybe they're worth $100. The pens are so slick. Yeah. I forgot what I was doing. Oh, I'm finding maximum. Second trace number what? 4, maximum. All right, so somewhere to the left, I'll scroll. To the left, to the left, to the left. Now, if you look at your x values, it's like 0.64. So you could just say like 0.6 if you don't want to scroll. And then to the right, I know the domain is 1, so I'm just going to put like 0.9. Yay, go me. Saves a little bit of time. And so notice this one doesn't give vertical lines, but it does give the arrows at the top. And so I'm saying somewhere between there, there's a high point. You hit enter, and it scans. And come on, big bucks, no whammies. Yeah. So now it says that. So I'll say that G has a local and absolute or global. I'm not going to count off if you use local and absolute. It's not a big deal. Local and global, though. What's? Yes. Well, it's also a local. So you want to say that it's a local for sure. It's a local maximum, and it's also a maximum. So local and global max of y equals 0.324. Now, is that your calculator's way of trying to say, I'm actually 0.3? No, there's enough variety of numbers there that you're like, okay, it's 0.324. And it'll be at x equals what? 0.75. Good. Notice there is 0, 0, 0. There's your 3 zeros. And then after that is another small number like a 1. So that is actually the right answer. Now, notice if you do go to 3 decimal accuracy, you're going to put 0.750. That's still equal to 3/4. So that's why we go to 3 decimals. Yeah.
My x says 0.749999.
Okay, so yeah, depending on which calculator version you have, hers says 0.7499999. And so in that case, when you see 0.74999, big number, that's your calculator's way of saying, hey, you got to round up. All right. So it's interesting. It's the same company, but we're getting different things. Yeah, you have the 0.749 as well. So anyway, you're the boss, remember, of your calculator, not the other way around. So the answer is x equals 0.75, which is actually what as a rational number? 3/4. 75 cents is 3/4 of a dollar. Okay. So you could put 0.75 or 0.750. Okay, so that's the local. Do we have any other local extrema? Can local extrema occur at endpoints? No. Do we have any absolute or global mins? Yes. G has, that's an ugly yes, has a, I'm just going to put min. It saves some writing because we know it means global or absolute. Has a min of y equals what? 0 at x equals 0 and good, and 1. 0 and 1. Can we write the range of this function? We haven't been doing that. Can we write the range of this function? We would abbreviate that R sub G instead of D sub G for domain. If we're finding absolute maxes and absolute mins, we should be able to, from 0 to, what was the high point? What was the absolute maximum? Not 1, but 0.324 with the bracket. So if you do an interval notation, you could do that. So once you find absolute max and min, it's easy to find, or once you analyze, I should say, absolute max and min, because not all functions have absolute maxes, as we've already seen. But you can find the range now, and not just the domain. Yeah. Yes. Yeah. All right. Any comments or questions on this fellow? Yeah. Okay. Cool. Cool. Oh, look at that. It's a perfect picture for National Boyfriend Day, right? You can give that to your boyfriend. Right. Autograph it. There you go. Nice. It's a cool sun. All right, hang on. I wanted to make this a white tip shark, so I'm going to outline it. I'm going to come back over here and then. Oh yeah, now it's a white tip. Okay, good. Any questions on that? Using the calculator for finding stuff, right? It's a tool. All right. So the next thing we're doing is we're going to kind of get not super into physics, but a physical application. Isaac Newton was the man that was motion guy, and he discovered calculus. But before calculus, which lets you to find instantaneous velocities, how fast things are moving at a single moment in time, before calculus and Isaac Newton and a guy named Leibniz, who's by my desk, you could only find average velocities between 2 points in time. That's what Galileo was doing in Pisa when he was rolling balls down inclined planes. He was trying to determine how fast they were going at a single moment, but all he was able to do is figure out their average velocity on a small interval of time. Okay, so in general, average velocity is a specific form of an average rate of change. We could talk about how anything changes. It doesn't have to be, wow, look at his position change. He's fast, right? We could say, wow, look at the temperature change. A cold front's blowing in, or something like that. So anything that changes, we can determine how fast it changes on average by knowing where it was in the beginning and where it was at the end, okay? So how would we figure out then average speed, which I'll go ahead and also say, that speed is a scalar quantity, which means it doesn't have direction. Velocity, you may have had this in your studies, velocity is made up of speed plus direction. Okay, so it's a vector quantity. So you could be going 100 miles an hour, to the left or to the right. The speed would be 100, but the velocity would be negative 100 if you're going to the left and positive 100 if you're going to the right. Okay, so there's a direction. But in general, to find the average speed, you take the total distance traveled, which actually is going to be over the elapsed time. The total distance traveled, I should add something here. It should be the distance traveled. It should be the distance traveled in one direction. One direction. Yeah, I miss them. Yeah, I really do miss them. I hope they do a reunion tour. Yeah, I don't think so either. But if it's not in one direction, we can talk about the displacement. So let me add that on there too. What is the difference between displacement and distance traveled? Are they the same? Yeah, displacement is directional. Distance traveled is not. Very good. So watch this. I'll just demonstrate it for you. I'm standing up here in front of you. I take 2 steps to your right, and then I take 2 steps back to your left, and I'm dancing, right? What was my total distance traveled in steps? I took 4 steps, but what's my displacement? 0, okay? So displacement is your net change in position, and your distance traveled is the accumulation of motion in any direction, okay? So if you take your total distance in one direction, or your net change of position displacement if you're traveling in 2 directions, and you divide it by the elapsed time, you get your average rate of change of position, which we call average velocity. Por ejemplo, if you drive from here to a point 130 miles away, we'll just keep it in one direction. You're driving on I-35. Let's say you're going from here to Waco to visit my son for some weird reason, okay? You travel 130 miles in one direction, and it took you 2 hours to get there. You could determine your average rate of change of position, right? It would be 130 miles divided by 2 hours. 130 divided by 2 would be 65. And notice your units are miles divided by hours, which, of course, we read that as miles like a kitty cat per hour. Good, miles per hour, which, of course, has become not M divided by H, but in our society, we use P, right? MPH. Now, does that mean that you had to be going 65 miles per hour the entire time? No. I mean, you started in your driveway going how fast? 0, right? And then when you pulled into Waco, you stopped, hopefully, and you were 0 when you stopped. So your speeds varied quite a bit in through there, right? And then you're going like 70 miles an hour in some parts and whatever, 85 in another, I don't know. But your average speed was 65 miles per hour. So that is an average rate of change of position. We know something at the beginning. We're at 0 miles traveled in 0 hours. And we know something at the end. 2 hours later, we've gone 130 miles. So we find the rate of change. Okay. In general, here's how we find the average rate of change of position, which is also called the average velocity. Okay? It would be the distance I was at time 2 minus the distance I was at time 0 all over the elapsed time 2 minus 0. So this is basically, if you remember from Algebra 1, this is y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. What was that the calculation for? That was the slope of a line segment, right? And you might have abbreviated it delta y over delta x, where delta stands for rich, fertile crescent, yeah? Sure. No, it stands for change in. But there are river deltas that are very rich. Yeah. Rich. Yeah, I'm sorry. Yeah. River deltas versus scientific deltas. That means change in y over change in x. Yeah, we call this has a name now. Whether you're doing it with function notation, which is what we have here, or y notation, or you just abbreviate it like that, we call that the difference quotient. And you'll be hearing that quite a bit, especially if you go on to take calculus. The difference quotient. Sometimes I like to just abbreviate it DQ, but when I do that, then I get hungry, and I want a Hunger Buster with cheese and a Blizzard. So then I lose my focus. Like Reese's peanut butter, Blizzard. Okay. All right. Difference quotient, DQ. Now, when you had Algebra 1, your lines were boring, right? You were probably bored in Algebra 1 because you could pick any 2 points on that line, And when you calculate the slope betwixt the two, rise over run, which is delta y over delta x, between any 2 points, you're going to get the same value, correct? The slope of the line between any 2 points is the same as the slope of the line at any point. That would be like if you travel to Waco 65 miles per hour on cruise control, including starting out of your driveway that way, like, whoa, dog, right? That's impossible. You can't instantaneously go 65. But if you've ridden the Aerosmith rock and roller coaster, it comes darn close, right? Poltergeist, does it do that too? It takes off real fast? Oh, wow. Where's Poltergeist at? In San Antonio? Oh, man, I got to get there. Okay. I haven't been there in a long time. You feel like you're going to hit the rest of the roller coaster. Really? Okay. All right. Poltergeist. So if we have a less boring function, phones away, please. Thank you. Yeah. If we have a less boring function, what does it mean to find the average rate of change between those 2 points? X sub 1, y sub 1, x sub 2, y sub 2. If we calculate the slope between 2 points, it's still going to be the slope of a line. So we're still going to be finding the slope of the line that would connect those 2 points. Guess what we call that kind of line that intersects the graph at 2 places? It has a name. Imaginary line. That's a good effort. I like that. Imaginary. Where's the line? I don't see it. It's imaginary. No, I see that one. We call this you might have had it in geometry, a secant line. A chord of a circle is a secant line segment. Did that ever come up in geometry? Okay, good. So a secant line. So basically, finding for something that's not linear all the way, if I can find the slope of the secant line between 2 points, that would be enough, or the same calculation, to find the average rate of change of that function betwixt those 2 points, okay? So here it is, the average rate of change of a function, f of x, between two x values, x equals a and x equals b. That would be on the interval from a to b. That's another way to write it. It's going to be average rate of change, a little bit of Irish in here this morning. Average rate of change is delta y over delta x. And I'm going to stop trying to do an accent because it was turning into something else. F of b minus f of a over b minus a. That is your what? What do we call that? It is the average rate of change. It's the difference quotient. And it also gives you the slope of the what? Secant line. They're all the same thing. The difference quotient is, from the Newtonian perspective, the average rate of change of a quantity. From the Leibnizian perspective, which is Leibniz back there, it's the slope of a secant line. Okay? And you'll get into that a little bit more if you want to take calculus. But they all mean the same thing. So whatever quantity you're measuring on the y-axis, let's say we're measuring temperature in degrees Fahrenheit, over time in hours, if I take the temperature at one time during the day, and then I take the temperature again later in the day, temperatures don't follow a nice linear path. If I found the average rate of change between those, that would give me the average temperature during that time period. Okay? It would give me the average temperature during that time period. And it would end up being the slope of that secant line that connects them. All right, so let's try it out. Example 4. Sketch the function without a calculator. You have it in front of you, so if you need to verify, that's fine. There it is, and then find the average rate of change on the following closed intervals. All right, so let's sketch it first. What's the parent function here? X squared. And what does the minus 4 do to it? Moves it right 4. So the vertex was at 0, 0. Now it's at 4, 0. And it's going to open up this way. And then it's going to open up that way. It has symmetry through that vertical line, through the vertex. All right, so that's enough to get an idea of what we're doing. So now we want to find the average rate of change of that parabola on the closed interval from x equals 2 to x equals 4. Now notice it says x epsilon. That doesn't even have to be there. That's just to clarify. If I just said on the interval from 2 to 4, that means x interval. So that's an x value 2, that's an x value of 4. So let's see what that would look like. X equals 2 would be somewhere right in the middle there. So it would be that, and then here's 4, which we know is the vertex. We're essentially finding the slope of that line, which is a what line again? Secant line. Good. Slope of the secant line. So let's go ahead and set it up. We're going to label our expression. So I'm going to put average rate of change. And you can abbreviate that average ROC, like the mythical bird, R-O-C, average rate of change is, and here's what I want to see. When you set these things up, I want to see the difference quotient. So our function's name is f. So here's what you're going to write. F of 4 minus f of 2 all over 4 minus 2. Okay, so that's basically, we have two ordered pairs. If you want to come out to the side and write it, 2f of 2 is one of the points, and then 4f of 4 is the other point. So all we're doing is algebra 1 there, right? Changing y, we're changing x. Now, you did learn in algebra that it doesn't matter which one you start with. So you could have done f of 2 minus... Oh, I forgot we're on assembly schedule today. Yeah, advisory schedule. Thank you for... Wow, okay. That took me by surprise. We'll stop right there, I guess. Have a great rest of your day.